let's take a look at how we integrate fractions again, but this time the denominators, we're looking at those quadratics in particular, some other ways of handling those when there's things on top. So, there are some standard integrals that we have, there are some non-standard integrals that we don't. This difference of two squares, a squared minus x squared and x squared minus a squared, they're not on the sheet of standard integrals. Okay? What you would do is, like we did yesterday, you'd use partial fractions. The bottom would become the difference of two squares. I would suggest, rather than doing that every single time, just memorise these. They're the missing standard integrals, if you like. And I just tend to quote them. The other quadratic ones are in the standard integral. So you've got the inverse tan for the sum of two squares. Then the other three involve the square root. And so the square root of a squared minus x squared, that's our inverse sine or our negative inverse cos. And then there's these two ones, the square root of x squared minus a squared, log of x plus, and notice the square root always matches in these ones. So it's the square root of a squared plus x squared. Again, the third over there is the square root of a squared plus x squared. But they are in the standard integrals as well. It's just those first two. So however you decide to come up with a way of remembering those ones. So x squared plus 4x plus 9. I want to create squared plus or minus squared. So basically we complete the square. So it's always going to be something squared plus or minus a number. So x squared plus 4x plus 9 would be x plus 2 all squared plus 5. So it's x squared plus a squared, inverse tan. Instead of x, I've got x plus 2. But it'll be 5 times it. And remember, with inverse tan, we have 1 over a out the front. So 1 over root 5, inverse tan, x plus 2 on root 5. Now when we do, if it happened to be 2x squared there, then I'd factorise the 2 out, because for our standard integrals, it always has to be 1x inside the square to be able to go, I'll go and use my standard integral. Okay, 3x plus 2 on the square root of x squared minus 4x plus 1. See, the first one just had a constant on top. This one doesn't. I have to break this up into two integrals. The way I break it up is like so. And you might be, whoa, how on earth did I come up with that? What I do is the first fraction, I'd simply write the derivative on top of the polynomial. So x squared minus 4x has a derivative of 2x minus 4. So I just put that on top. So that integral will always end up being du on root u, or du on u if there wasn't a square root sign. Obviously I can't change the question. So I need to put a fraction out the front to balance it out. I'm just looking at the x's. Had 3x, so therefore to change 2x back to 3x, I need to multiply by 3 on 2. But I've now changed my constant. So at this stage, before I write the second fraction down, I've got 3 on 2 times negative 4. Well, 3 on 2 times negative 4 is negative 6. I need positive 2, so I'll add 8 over. This one is where I'll complete the square on the bottom to turn it into a standard integral, so the second one. The first one, as I say, is just du on root u, which, remember, 2 root u. That was one of the non-standard integrals that's useful to remember. Okay. If you don't remember the du on root u, well, then what you would do with the first one, I'll do the substitution. X squared minus 4x plus 1. Du is 2x minus 4. So you end up with the du on root u. Now with the second one, I'll complete the square. So this one is the square root of x squared minus a squared. Square root of x squared minus a squared was the log one, wasn't it? It was the log of x plus. And remember, the square root will stay the same. So that's the square root of all that. So I end up with 3 on 2 times 2 root u. 8 lots of the log of x, well in this case it's x minus 2, plus the square root. Well, I know what that square root is because it was the original question. I didn't write down square root of x minus 2 or squared minus 3. I wrote the original x squared minus 4x plus 1 there. And let's put the u back in. So I guess if you do remember that du on root u, you can go straight to 2 root u. You don't need this line here. You just go straight to 2 lots of the square root of x squared minus 4x plus 1. That's why that's a useful non-standard integral to remember as well. This one here doesn't look like it's one of these questions, but in order to integrate it, we're going to turn it into one of these questions. And what I'm going to do is rationalise the numerator rather than the denominator. Okay. So I'm going to multiply by the square root of x plus 3 on x plus 3. And so it then turns into a question like the last one we saw. I've got x plus 3 on top and the square root of a quadratic on the bottom. I'll do exactly the same thing. Okay, first fraction, I want the derivative on top. That would be minus 2x minus 1. So I've got to make sure that's positive 1x multiplied by negative a half. That means my constant at this stage is positive a half. I need 3. So to get from positive a half to 3, I need to add on 5 on 2. I don't know why I put the 5 in the integral and the half out. So I could have just as easily gone 5 on 2 out the front. Doesn't really matter. But I'm going to have to complete the square on the bottom. Again, you'll notice I now have du on root u. I know that will be 2 root u. The second one, I'll complete the square on. Complete the square, this one's a fun one. Half the coefficient of x in this case would be negative a half. Got to be careful though. I need to end up with a negative x squared. So I know outside the perfect square, I'm going to have a negative sign to get the negative x squared. That therefore means I don't put negative a half inside. I put positive a half, because when we expand the whole thing out, I'm going to end up going negative times that, and we need negative x. Very careful with these negative x squared ones. Now to balance it out, at this stage, well, a half squared is a quarter, but it's actually negative a quarter. We want 6, which would be 24 quarters. So I need to add back in 25 quarters to get us to where we want. Okay, it's in the form of an inverse sine. Square root of a squared minus x squared. So okay, we get our 2 root u, inverse sine of 2 lots of, because a, you'll notice, is 5 on 2. Turn it upside down, 2/5. X plus a half, that's nice because now my fraction cancels out. And there we go. Isn't that a thing of beauty? You're going to love that. So as I say, the missing standard integrals that come in handy. Okay, 1 on 2a log a plus x. So if the integrand finishes with the x, then the primitive finishes with the x, a minus x. There's the other one. If the integrand begins with the x, then the primitive begins with the x minus. All right. So there's some questions out of Patel, our Cambridge as well. We'll just add those to our list of questions to do.